I'll tell you, Euclid, once this gizmo hits the math market, it's going to revolutionize the way people live. I can just see it now. No longer tormented by triangles. No longer trapped by the triad of tribulations. No longer trammeled by a trio of treacherous... Relax, will you? You've got great surge protection, and you've got wonderful battery backup, too. You don't have to worry about a little bit of lightning, you know. Unless, of course, it hits us. Oh, great. Well, I guess that's all the work I'm going to be doing tonight.
Where are you going?
Oh, you know that tree on the hill behind the math shop?
Yeah?
Well, it got hit by lightning last night.
No.
So I'm going to go cut it down because if we get another storm like we did last night, it could fall over in the wrong direction.
Hey, wait a minute. I don't want it to fall on the shop. Have you done any calculations?
Yes, I eyeballed it.
No. No estimating, please. We have to take accurate measurements. After all, math shop is in danger here.
Okay, I'll take measurements, okay?
Okay, good.
All right, well, let's just get the show on the road.
All right.
Hi, you're watching Math Shop, where we use mathematics to leap tall trees in a single bound. I'm Christine, and this is my knowledgeable math partner and gold medal math coach, Kanwal.
Hello.
And this is my highly motivated, highly charged, homemade computer, Euclid.
On this show, we deal with basic trigonometry, often referred to as trig, which is a lot easier to say.
Trigonometry is the branch of mathematics that began with the measure and ratio of the sides and angles of triangles. Today we'll look at the angles formed by triangles and show how they're related to the three sides.
In particular, we'll talk about measuring three trig ratios, the sine, the cosine, and the tangent. And we'll give you an easy way to remember how to calculate them.
We'll talk about something called the Sine Law and solve a few problems.
Stay with us. We're going to cover all the angles.
Whew, a math joke. Okay, let's get started. I'm going to need this.
Okay.
This.
What is this?
This?
Yes.
This, dear Kanwal, is called a clinometer. Okay?
Oh, okay.
What you do is going to measure all the angles we need.
All right.
What you do is you sit on the ground, and from the ground up, you look at the top of the tree. Then you flip it over, and then you read the angle.
Oh, great.
Okay, I gotta go.
Okay. Okay, wait a minute.
Huh?
While you're out there, don't forget to measure the dead tree on the other side of the math shop.
What?
Yeah, we need to take that one down too.
Okay.
Okay. See you later. Well, as we said, this is a question for trigonometry. First, we'll deal with the trig of triangles that have one 90-degree angle. Such an angle is called a right angle, and triangles that have them are called right triangles. This small square in this corner indicates a right angle, or 90 degrees. I can label this triangle A, B, and C. Angle ABC is a right angle. It's equal to 90 degrees. The other two angles are always less than 90 degrees. Any angle less than 90 is called an acute angle. Euclid, could you give us some more right triangles, please? No matter what shape the triangle, no matter how long or how short the sides are, if it has one angle equal to 90 degrees, it's a right triangle. And all the properties we will tell you about today apply. In every right triangle, the side across from the right angle is always called the hypotenuse. The other sides of the triangle, often referred to as legs, also have names, but the names change depending on which of the two acute angles you investigate. For example, if I'm looking at angle A, then side AB is called the adjacent side, and the side across from angle A, side BC in this case, is called the opposite side. If, on the other hand, I'm talking about angle C, then side BC is now the adjacent side, and side AB is called the opposite.
Okay, Kanwal, I think I got all the measurements.
Good. Did you remember to get them for both the trees?
Yeah, I got everything I need. Okay, Euclid, incoming. These are the two trees we have to cut down. The tree on the flat is 31 meters from the edge of the rose garden, and the edge of the garden is 7 meters from the math shop. I sighted from the edge of the rose garden to the top of that tree and measured that angle as 48 degrees. The other tree, the one that got hit by lightning, is on a hill, and so I measured the angle formed by its trunk and the hillside and found it was 112 degrees. The trunk is only 19 meters from the shop, and when I sighted from the shop to the top of that tree, I found an angle of 35 degrees. Now, it happens that we have neighbors on all sides, so we can't follow the trees away from the shop. But let's find out if they'll hit the shop when they come down.
Oh, wait a second. We still need to understand a few more basics. The relationship between angles and sides of a triangle provides some very helpful values. Let's look at angle A. It's formed by two sides, side AB and side AC. Side AC is the hypotenuse. Side AB is the adjacent. And side BC is the opposite side. The laws of trig say that if I divide the length of the opposite side of an angle by the length of the hypotenuse, I'll get a value called the sine of angle A. So sine of angle A is equal to opposite divided by the hypotenuse. In this case, BC divided by AC. This is called a trig ratio. And notice that sine has been abbreviated to SIN. Now, Euclid's going to help explain this ratio in a bit more detail. Here's the triangle we were looking at. We find that angle A is 53 degrees, and let's say the length of the hypotenuse is 5 centimeters, and the length of the opposite side is 4 centimeters. The ratio of opposite over hypotenuse is 4 over 5, so the sine of angle A is equal to 0.8. Now, watch what happens when we keep the measure of angle A constant and stretch the length of its legs. Euclid, double the length of the opposite side so that it is 8 centimeters. Angle A is still equal to 53 degrees. The opposite side is now 8 centimeters, and the hypotenuse is now 10 centimeters. That means the ratio of opposite over hypotenuse is equal to 8 over 10, and I find that the sine of angle A is still 0.8. One more extension, Euclid, please. And once again, I note that as the lengths of the legs change, the sine does not change for a given angle. There are other such ratios. The length of the adjacent side divided by the length of the hypotenuse is a ratio called the cosine. Cosine angle A is equal to adjacent divided by the hypotenuse. In this case, AB divided by AC. Now, cos is sometimes abbreviated as COS. And lastly, a value called the tangent, or tan, and tangent is found by opposite divided by the adjacent. So tan angle A is equal to opposite divided by adjacent, and in this case BC divided by AB. You should note that the sides used in the ratio change depending on which angle I consider. If I look at the trig ratios for angle C, so change this, the names of the sides change. So this now becomes the adjacent side, and this is the opposite. And when the names of the sides change, I must rewrite my ratios. So this changes to angle C. So now, sine of angle C is opposite over hypotenuse, which is AB over AC. Cosine of angle C is adjacent over hypotenuse, BC over AC. And tangent of angle C is opposite over adjacent, or AB over BC.
These three ratios, the sine, cosine, and tangent, form the basis for trigonometry, and it's best to memorize them. One way to do this is to use the acronym Sohcahtoa. It stands for sine opposite hypotenuse, cosine adjacent hypotenuse, tangent opposite adjacent. And if you have any trouble making Sohcahtoa stick in your mind, try making up a nonsense sentence to fit these first letters. Something like, she offered him cheese and herring to operate airplanes. It doesn't matter what the sentence is or that it makes no sense. In fact, the goofier it is, the easier it is to memorize.
Okay, now let's take a look at our tree problem.
Okay. Yep. Oh, wait. Problems, you mean, plural.
You're right. There are two trees to cut down, but each must be handled differently. Let's first take a look at the tree on the flat. Euclid, could we see the sketch, please? One of the strategies on the problem-solving poster is to sketch the situation. And that's exactly what we did when we were gathering the information. Using the clinometer, Christine measured the angle formed by the ground and the line of sight from the edge of the rose garden to the top of the tree, and found it was 48 degrees. She couldn't get right up beside the house to take the sighting because the rose bushes were too prickly. And she also measured the distance from that point to the trunk of the tree, and found it was 31 meters. Euclid, please could you convert this into a geometrical rendering? The top of the tree is labeled T, the base is B, and the point at the edge of the garden is labeled G. The edge of the math shop is labeled H. We need to find the length of TB, the height of the tree. Angle G is equal to 48 degrees. GB, the distance from the edge of the garden to the bottom of the tree, forms the adjacent side of angle G, and it is equal to 31 meters. Now, we know the measurement of angle G and the length of the adjacent side, but we don't know the length of the opposite side. So, we need a trig ratio which involves the opposite of angle G and its adjacent. Remember Sohcahtoa? It isn't so, S-O-H, and it isn't Ka, C-A-H. It has to be Toa because here's our opposite and our adjacent. So we use the tangent ratio. Now, our equation is tangent of angle G is equal to opposite over adjacent. In other words, the tangent of 48 degrees, tan 48 degrees, is equal to the opposite, or BT, over the adjacent, 31. Now, I can solve this either using trig tables, which I can find in the back of most math textbooks, or better still, use my calculator to find the tangent of 48 degrees. But before I do that, whenever you use the trig ratios, make sure that the calculator is in the degrees mode, not radians or grade mode. Now, to find the tangent of 48 degrees, I press 48 tan, which gives me 1.1106. Next, I multiply 31 equals, which gives me the answer, BT is equal to 34.4 meters. The distance from the trunk to the math shop is 31 plus 7, a total of 38 meters. So the tree won't hit the building. But the roses are going to take a beating.
That's okay. They need a little pruning anyway. We'll do the other tree problem in a minute, but first, let's take a closer look at the sine, cosine, and tangent ratios. Another way to make these ratios more comprehensible is to study them visually. Now this is my latest invention. I was just putting the finishing touches on it last night when the lightning knocked the lights out. I call it the Trig Trainer, and it measures the sine, cosine, and tangent of various angles. Let me demonstrate. The inner circle is really a 360-degree protractor. I can use the Trig Trainer to form angles of different degrees by rotating the bar around the center point. We always begin with the bar in this location, 0 degrees, and rotate it in a counterclockwise direction. The angle is formed between the initial and final location of the bars. For example, this is a 45-degree angle, and this is a 67-degree angle, and this is a 90-degree angle. We can also use it for angles greater than 90 degrees. For example, this is an angle of 110 degrees, and so on. The Trig Trainer always forms a right triangle. The hypotenuse formed by this bar is always equal to 1. Once I set the trainer to a particular angle, like, for example, 39 degrees, I can measure the sine of 39 by reading the y-axis. It's about 0.63. Likewise, I can read the cosine on the x-axis, about 0.78, and the tangent on the outside grade here. It's about 0.8. Let's concentrate on the sine ratio for a bit. I'm going to use the Trig Trainer, and Euclid's going to plot a graph. Stand by, Euclid. I'm going to give you readings as I go. Here's the first one. We'll start with 0 degrees. The sine of 0 degrees is 0. 30 degrees has a sine value of 0.5. 45 degrees has a sine value of 0.71. 60 degrees has a sine value of 0.86. And 90 degrees has a value of 1. As the angle increases from 0 to 90 degrees, the value increases from 0 to 1. Euclid, connect the dots. This pattern continues on the other side. 135 degrees has a value of 0.71. The sine of 180 degrees is 0. So, as the angle goes from 90 to 180 degrees, the sine decreases from 1 to 0. Continue the graph to 360 degrees, Euclid. Now, that was sine. Let's do the cosine. The cosine of 0 degrees is 1. 30 degrees has a value of 0.86. 45 degrees has a value of 0.71. And 60 degrees is 0.5. As the angle increases from 0 to 90 degrees, the cosine decreases from 1 to 0. And as the angle goes from 90 to 180 degrees, the cosine becomes negative. Now, complete the curve and see how it compares to the sine curve. Now we read the tangent on this vertical line here. Let's look at our 0 degree angle again. The value of the tangent is 0. Let's look at our 30 degree angle again. And the value is 0.58. Now let's look at 45 degrees, and it's 1. As we've seen, for the sine and cosine curves, the values never go higher than 1. But as we go past 45 degrees, the tangent goes beyond 1, and we can no longer use the Trig Trainer to find the tangent. We'll get Euclid to help us out. Euclid, plot the tangent curve. as you can see, as we get closer to 90 degrees, the tangent increases faster and faster. In fact, this line goes to infinity. The pattern is the same for the other 3 quadrants. You don't have to memorize these graphs in order to do trigonometry, but they do show how the 3 values, sine, cosine, and tangent, are interrelated.
And now we're ready to look at the problem of the other tree, the one on the hill. Remember, we said that this requires a different method of calculation.
That's right. Euclid, show us the sketch, please. And now, a geometric rendering, please. Thank you. Now let's see what we know about this triangle. I measured angle H as 35 degrees, and the length from the math shop to the trunk of the tree, side HB, as 19 meters. We also know that because it is on a hillside, the angle formed by the slope and the tree trunk is not 90 degrees. I measured that and found it was 112 degrees.
The big difference between this triangle and the previous one is that it has no right angle, so it's not a right triangle. Because it isn't a right triangle, the trig ratios we have used up to now won't help us. Instead, I must use something called the sine law. The sine law states that if you divide the length of a side by the opposite angle, this ratio will be the same for every side in the triangle. The inverse of this is also true. Let's check the sine law with an example. In this triangle, angle A is 18.6 degrees and side A is 2.0 centimeters. The ratio of 2.0 to the sine of that angle is 6.3. If I perform the same calculation for the other 2 angles, I get the same result, 6.3. Remember, the result 6.3 is the same for all 3 ratios, but these results of 6.3 are unique to this particular triangle. If we did the same sine law calculation for another triangle, it would give different results. But now we can get back to our problem. In this problem, we know 3 things. Angle B is 112 degrees. Angle H is 35 degrees. And the length of side BH is 19 meters. The sine law deals with angles and their opposite sides. Side BH is opposite angle T. If we want to use the sine law, then we need to find the measure of angle T. So we'll do that first. In a triangle, the sum of all internal angles always equals 180 degrees. That means that angle T is equal to 180 degrees minus the other 2 angles, 112 degrees plus 35 degrees. Therefore, angle T is equal to 33 degrees. And now we have everything we need to solve the problem. First, I'll add this information to the sketch and label the side of the triangle we're trying to find, which represents the height of the tree. I'll call it X. This is X, and this angle here is 33 degrees. So, now we can use the sine law. And according to that law, 19 over the sine of angle T is equal to X over the sine of angle H. Now, I substitute the measure of the 2 angles, and I get 19 over sine 33 degrees is equal to X over sine 35 degrees. I isolate X by multiplying both sides by the sine of 35, and I get X is equal to sine of 35 degrees times 19 over sine of 33 degrees. Now, I'll use my calculator to solve this. Clear, 35 sine times 19 divided by 33 sine equals, so the height of the tree, X, is equal to 20 meters. And since the tree is 19 meters from the math shop, the tree will hit the building if it comes down all in one piece.
Don't worry about it.
What do you mean, don't worry about it? If the lightning hits the tree again, we're history.
That's right. But lightning never strikes twice in the same place. I mean, what are the odds?
Well, I'll figure it out.
Yeah, I thought you'd say that. Well, thanks for tuning into Math Chop, and join us next time when we make mathematics Ooh, electrifying.
Oh, goodbye.
Kanwal.
Yeah.
I can't believe this happened again. Why don't we get the candles out?
Where are they?
I think I've got some over here. I know. Why don't we have a seance?
Okay.
I know. We can get like the spirit of Pythagoras or something. Pythagoras and Elvis to
And
come.
we'll use a Trig Trainer.
Yes, and then they can move the Trig Trainer around.
Oh,
We
I
can
like
find out
that. I like
different
that.
angles in history or something.
Okay, where do we start?